So we need an Alice, a Bob, an Eve, and someone just to be himself. So we've got Hanyu is Alice.
I'll be myself.
You want to be yourself? Okay. Memo, how about you be? You'll be Bob. Okay. So Alice, you're going to go right there where Alice was, and then Bob, you're going to go over where Bob was. Right. So, are you Eve? Yeah. So Varun is himself, and Boom is Eve. So, Alice and Bob, let's assume that they've set up a public key encryption mechanism with each other. So they can talk freely, and the class and Eve just pretends that we can't hear what they're saying, right? So Alice, tell Bob something. Pardon?
Number?
Anything. Like it could be number, could be English. What you had for lunch today.
Chocolate.
Okay. Bob, did you hear that? Okay, speak up.
Chocolate.
Okay, right? That's public key encrypted, so the class and Eve does not know that Alice had chocolate for lunch. That's a very confidential piece of information, right? What we're going to do now is we'll bring Eve in. So Eve, you're going to step right in the middle here. Now, this is over the internet, so Alice, you can't actually see Bob, right? You just see the connection that happens between you and Bob. So as far as you're concerned, Eve has now stepped himself right in the middle here. This is your Bob. Bob, you can't actually see Alice. Eve has now stepped in the middle of the connection here. This is your Alice, right? So now, you're going to set up a public key encryption with who you think is Bob, and you're going to tell who you think is Bob what you had for lunch. Right? Bob got that? Now, he's going to set up public key encryption with the real Bob who thinks he's Alice, right? And now you're going to tell Bob what Alice had for lunch.
Chocolate.
Right? So Bob and Alice can still communicate. Now Eve knows what they had. That is what's called, quite aptly, a man-in-the-middle attack. Right? So you have someone, or a machine, that will set up a public key encryption to both Alice and Bob, and each thinks that Eve is the other, and that way they can circumvent public key encryption to get the message. Any questions on that? Yes. The answer is they shouldn't be. In theory, they could be. Like any switch, any server that the packet passes through could set up this man-in-the-middle attack. So the regional internet registries really shouldn't, because they're run by international consortia. So they have to answer to each other. They wouldn't do that. But say if they want to set up something like that on U of T's servers, they might do that. So when you go connect to something through HTTPS, U of T could, in theory, pull a man-in-the-middle attack on you, right, using one of their router switches. Yes?
Are man-in-the-middle attacks, is that like putting your own soft-in-the-middle software? Is that like a hardware attack, like plugging a wire in where it shouldn't?
Good question. It is almost always a software attack. I think we have everyone, so we'll shut this. Almost always a software attack, so almost always, say if you can hack a router, you can change the software of that to, rather than just passing it on as it should, setting up public key with both, and then eavesdropping and passing it on. It could be a hardware attack. You could replace a good router with one that you've created specifically to do that. But usually it's software, and it ultimately boils down to software, right? Because the one you created is software. Other questions? Yes, Juliet. Excellent question. The answer is no, you can't. And the reason for that is keys are used for different things. That PPK we created is for SSH. That is usable to SSH in, and that is something that we have to download using HTTPS, a separate protocol that we then use for SSH. If we could get that key, then yes, we could potentially modify the website. So yeah, public key, if we put a man-in-the-middle attack for public key encryption on SSH, then you could, and you could get the keys. And that is a fairly dangerous thing. Actually, no, that was incorrect. You can't get the keys. The reason for that is, let's go back to our little Excel demo. So we have right here different keys each time, right? So normally in HTTPS, you generate new keys each time. Bob makes a new P and Q, Alice makes a new M. right? So in HTTPS, you connect with these new P's and Q's and M's. When you're done the connection, you throw them away. With SSH, you use the same key each time. So in order to do a man-in-the-middle attack for SSH, the man-in-the-middle would have to know the private key of both the server and the client. Sorry?
That could happen.
Well, that could happen, but if you know that, then there's no need to do the attack. Well, actually, I guess there kind of could be. You could find out what data is being transmitted, but you can also just put a logger on the server. Yeah? Yeah, I mean, there are definitely some instances of that, and one of the documents that Edward Snowden leaked showed that the NSA in the United States has been working to try to crack this public key encryption and crack secure socket layers, which is what it's based on. So if they do succeed in that, then they would have a way of finding out the private keys of servers and potentially clients as well. I don't know that they have. That's not been, to my knowledge, publicized widely, but for all we know, they could have. Right? What it would, in all likelihood, still take, though, is a lot of time for them to do the computation. Yeah. But yeah, so for HTTPS, you can do man-in-the-middle because you throw away the keys each time. For SSH, you cannot because it's the same key. They're installed in that file on the client and on the server. So, we have now seen Eve institute a successful man-in-the-middle attack. How might we counteract this? Right? The way we can do that is, yeah, so try to find the source. That is actually a little bit difficult in practice because unless you know what the key this server is supposed to be sending is, you can't tell that it's improper. You can't tell which hop along those like 20 or 30 hops it takes to get to your site is the one that's taking or that's doing this attack. Sometimes you can do a trace route, see which one takes longer, because this does involve a fair bit of computation. We saw Excel chugging away there. And in that case, you can try to, or you can get one that's likely going to be the cause. But that's iffy because some switches are just busier, right? So it's very difficult to counteract it that way, but potentially doable. So a proxy server can work one of two ways. It can be unencrypted. In that case, you're sending it through the proxy server in an unencrypted manner, and the man in the middle would have to find which path it's going through with the proxy server. So it might make a different path. It might take your communication out of the path of the man in the middle. If you're using an encrypted proxy server, which you should usually do, in that case, the proxy server itself actually is an authorized man in the middle. You connect via HTTPS to the proxy server, it will connect via HTTPS to whatever you want to connect to. So in that case, it also changes the path, but adds a level of man in the middle that you accept. Other questions? Okay. So what we do in practice is we bring in what's called a certificate authority. That's where Varun comes in, right? Varun, wave to the class, right? He looks like a really trustworthy guy, eh? So let's say Varun is so trustworthy that Alice and Bob both trust him with their private data. Not necessarily with it, but with saying who is legitimate. So Varun, maybe step over here so you're not in the projector. So Varun is going to keep track of the certificates, is what it's called. A certificate is a piece of data that both Alice and Bob are going to have. It's a digital one, but it's like a paper certificate. And Varun gives them that, and it says, yes, this is actually Alice, yes, this is actually Bob. And it has like a serial number on it, right? So Alice wants to check if it's Bob she's talking to. Bob will send a public part of his certificate. She will send that to Varun. Varun says, yes, this is Bob. He'll send it back, and then Alice knows it's Bob. Bob will do the same thing, right? So let's try that for a simple communication. So Alice, you're going to set up a public key encryption with Bob to tell him something, okay? So your public key encryption is now set up. Bob has sent you his certificate, right? So what are you going to do with that? Yeah, so Varun, you get this certificate from Alice. She says this should be Bob, right? You know which certificate goes with whom. Is that Bob? Yes. Yeah, and you send that back to her. Alice says, okay, that's Bob, I trust you, right? And Alice is going to send her certificate to Bob. Bob, now you have Alice's certificate. What do you do with Varun? Right? He says yes. Now you know that it's Alice. You have both authenticated the other person, and now you can communicate via public key encryption, right? Enter Eve. So Eve, step in the middle there, right? Now Eve is going to pretend to be Bob to Alice, pretend to be Alice to Bob, right? So Alice, you're now going to set up a public key encryption with Eve, who you think is Bob. Okay, so you've done that. Now Eve is going to send the certificate along. Right, so you have that, and now what are you going to do with it?
Can I ask?
Yeah.
Is this
Nope.
Bob? Okay.
No.
And Varun says no, right? And Alice says, oh no, that's not Bob, terminate the connection. Right? So by adding this sort of fourth party, this trusted party, that's the certificate authority, we can then authenticate that we're actually talking to who we're supposed to be talking to. And that will prevent man-in-the-middle attacks. All right, thanks, guys. Any questions on certificates in general? Alex?
Isn't that system pretty bad? Because can't the fourth party simply be compromised?
That's a good question. So what Alex asked is, isn't that system bad because the fourth party could be compromised? The answer is yes, it could be. And that's why certificate authorities have very rigorous standards by which they must uphold. So they have to have very secure data centers, they have to have very high security on their servers, and they have to go through all kinds of legal hoops to be set up as an official certificate authority. And there are governing bodies that say which one is and which one isn't. Once they've done all that, then it's assumed that they're way more secure and so that they can be trusted. But you do have to have that level of trust at some point with a certificate authority. If that trust breaks down, then unfortunately it's not possible to authenticate, right? Because when you think about it, two people on the opposite side of the world connecting with electrons and wires, there are a lot of ways that you can spoof another user. So it's only by having some kind of base level of trust that you can build up the entire web of trusted networks that we use for public key encryption. Excellent question. As asked, aren't there trustless alternatives like Bitcoin? The answer is yes. Bitcoin works by creating essentially a very difficult to detect or to figure out set of keys. I don't know the exact mathematics behind it, but a Bitcoin has a set of numbers that's very difficult to compute. It satisfies a number of rigorous mathematical standards that most numbers do not. And that's how Bitcoins enter circulation, is people go on large computers and find a new Bitcoin that works. And then that becomes a Bitcoin and they can sell it and they get money by doing that, right? That's Bitcoin mining. That is a very computationally intensive process, and that's something that we cannot do every time we want to connect to a server privately. If we could do that, then an attacker could do that and figure out what we were, or what our private keys are. Right? Does that answer your question? So what we will do, we'll do this not right now, we'll save this for a bit later, but this shows how we set up a secure socket layers on our Python server. So to quickly go through what actually happens, we install some things we need, and then we install a Python module that extends our HTTP server to be HTTPS. And now we need to create an SSL certificate. Our SSL certificates cost money, because that certificate registrar has to go through all kinds of hoops to be certified as a registrar. So they have to get some money back for doing that. So creating a third-party trusted signed certificate costs money. That's why we're not going to do that in this class. We're going to do what's called a self-signed certificate. That's basically saying, yes, I am saying that I am me. That's not secure because we don't have that trusted third party involved, and it'll give a browser warning when we do it, but it'll allow us to do HTTPS. So what we do is, we're first going to generate a private key. That's what this does, right? And then we're going to create what's called a certificate signing request. That's a file that we can send to a registrar that says, I am me, I live here, I am at this address, I work for this company, create me this certificate. The registrar is then going to look into that company and make sure that you are who you say you are, right? They don't just issue certificates to anyone who claims to be that person. And then they'll say, okay, you are who you claim you are. I've done the background check. That's also why it costs money. They have to do that. And then they will issue a certificate. In this case, we're self-signing, so we use this command to generate our certificate, and it uses our private key, it uses our certificate signing request, and it creates a CRT file. That's the certificate. And then in our Python, we're going to import the HTTPS server, and we'll tell it where the certificate and the key is, right? So we'll actually go ahead and do that in a bit of time, but that's how we're going to end up setting up HTTPS. Questions on that?